In this video, I am going to implement quicksort algorithm in parallel. Let's first see the steps of quicksort algorithm and implement it sequentially to get familiarized with the algorithm and then implement it in parallel. Quicksort is one of the most efficient algorithms out there. In fact, this algorithm often regarded as one of the top 10 algorithms in 20th century. There are 4 steps to quicksort algorithm. In the first step, we pick an element called pivot element. Now, there's nothing special about this element in general, and you can pick any element as pivot element, but there can be slight performance difference based on which element we pick as the pivot element, but this effect usually ignore. So that's the first step. In the second step, we arrange the input array in a way that all the elements which are lower than the pivot value to be in lower part of the array, and all the values which are higher than the pivot value to be in upper part of the array. So in this demonstration, values which are lower than the pivot values are represented by green cells, and values which are higher than the pivot value represented in blue color elements or blue cells. If you take one portion, either lower part or the upper part, there will not be any relative ordering between elements in one portion, but what we know is that all the elements in upper part is higher than the values in the lower part. That's only the thing that we know after second step. We will get back to this point in little later. In the third step, we are making recursive call to same sort function with lower portion and the upper portion of the array. And in the final step, we will take the results from the recursive call and prepend the results from the lower part before the pivot value in the results array, and append the results of recursive call with the higher part after the pivot value. So these are the basic 4 steps that we are going to follow to implement the quicksort algorithm. Let me quickly go through an example to showcase these steps. Let's say we have an array with 10 elements as shown in this slide and apply the steps we have just discussed. Let's pick the first element in the array as pivot value. In most of the implementation, this is the usual case. We pick the first element in the array as the pivot value for this iteration or for this quicksort function call. Then in the second step, we have to arrange the input array in a way that all the elements lower than the pivot value would be left to the pivot value or would be in lower part of the array, and values which are higher than the pivot value to the right to the pivot value or in upper portion of the array. So if we do that to this input array, the outcome would look like this. Notice all the values left to the value 8 are smaller than it. Also notice that if we took one portion, there's no relative ordering. We have simply copied the values to each parts in the same order we found them in the input array. That's all. That's why value 3 appears as the first element in the lower part, because it's the first element which is less than the pivot value in the original array. That is the same reason why value 2 is appearing at the last of the lower part. You can observe the same for the upper part as well. And then in the next step, all we have to do is to call same quicksort function with lower portion and the upper portion from the previous step. So when we call quicksort with the lower part and again pick the first element as pivot value, for this iteration or for this recursive function call, 3 will be the pivot value. And then if we arrange the input array, the output would look like this. Notice at this point, the array portion for that recursive call seems already in order, but there will be recursive calls using each portion of this stage as well, because we usually do this recursive call until there is only 1 or 0 elements in the array. In similar way, there will be recursive calls for the upper portion or upper part of the original input array as well. Okay, now that we have clear idea about how quicksort algorithm works, let's first implement this algorithm sequentially. So let's name our function as sequential quicksort. This function will return list of elements, and also it will take the list of element as argument as well. This is to facilitate the recursive function calls. So inside the function, let me quickly comment 4 steps that we are going to follow here. So in the first step, we have to select the pivot value. Then we arrange the input array as we discussed. And then we will make recursive calls with lower part and upper part. and finally arranging the results of recursive calls into the results array. Now before any of these tasks, we can have the recursive function return condition, which is if the array has less than 2 elements. In that case, we can return the input array itself. Then let's implement each of these steps. So first, let's pick the pivot element. Now there are several ways we can do this, but I prefer to have another list and store the pivot value as the first element in that array. I'm doing this because when the recursive calls return, we can simply add the results either before the pivot value or the after the pivot value easily using standard algorithms. So I'm going to have array called results here, and then I'm going to pick first element of the input array as the pivot value and transfer that element to the results array. For that, I'm going to use std splice function. Std splice function transfers element from one list to another. Now with this std splice function, there will be no any copy or move operations. Only the internal pointers of the list nodes are reappointed. So that's about the split function. Then here we can call split function on results array and give where we need to store the pivot element in the result array, which is at the beginning, and then the array to copy the value from and which element we want here, which is first element in this case. And then we can simply assign that value, the first element in the result array, as the pivot value in this way. Now this is a bit different from what I explained in the demonstration. There you can see I have kept the pivot element in the input array itself and arranged the lower and upper part beside the pivot value using the original array itself, but practically having pivot value in a separate array is much easier for our later stages. So if I demonstrate what I have done here, it would look like this. We have the input array, and then I have removed the first element of that array and store it in a separate array and pick it as the pivot value. That's what I did in the code. So after this point, remember there are one less element in the original input array because we have copied the first element to a result array. Then I have to arrange the remaining elements in the input array so that all the elements less than the pivot will be left side of the array and the rest are on right side in the array or right side to the pivot value. So how to do that? We can easily achieve this using std partition function and lambda expressions. Std partition function takes 3 arguments, start and endpoint to the array we need to arrange and the predicate which govern the partition process, and it returns the pointer to divide point in the input array. So here let me give our input arrays begin and end pointers as the first 2 argument. Then for our predicate, we will be using lambda expression which check whether the element is less than the pivot value or not. This function call will arrange the element in input array as we need it to be. So after the partition function call, input array in this demonstration would look like this. Notice the black vertical line in the middle, which is the pointer returned from the std partition call, and all the values left to this line is less than the pivot value, and all the values right to this line is higher than the pivot value, just as we expected. Okay, now first 2 steps are done. Next, we have to recursively call this function again for each of the parts divided by the pointer returned from the std partition. Since we need to pass the list as argument to our next recursive function calls, we need to move one part of the input array to separate list so that we can call recursive function separately for each of these parts. So here let me declare another list called lower list, and then we can transfer the lower part of the input array, which is in between the begin and midpoint pointer returned from the std partition call, to create this new array. So after this step, lower part of the original input list is in the new list and upper part is remain at the input array. Then we can call our function recursively for each of these parts in this way. Now we have completed 3 steps of our algorithm. Notice at this point, return values of recursive call are stored in new lower and new upper list. Now all we have to do is to prepend the results list with a new lower part and append the new upper parts so that pivot value will be the one dividing each of these portion. That's it. Now we have our own implementation of quicksort algorithm. Now how to convert this into a parallel implementation? Well, it turns out to be very easy. So let me copy our sequential implementation and rename it as the parallel quicksort. Now what I'm going to do here is to make one of the recursive function calls to be executed as an async task. Then we can take the future associated with that async task and call get function to wait until the data is ready. So here let me declare the std future. We can simply construct here using the what return from the async task. So let's do it here. For that we can simply put a bracket and launch the recursive call using std async task in this way. It will call parallel quicksort function on upper part of the partition, which is now at the input list. Make sure to use std_move to send the input to the async task as well. That's about it. Then we have to wait on the future. So let's call that inside where we use the splice to append the elements. So that's it. This is our parallel version of quicksort algorithm. Of course, there are multiple ways to implement parallel quicksort and there are more efficient ways to do it as well. But I think this version gives you a clear idea how to use or how to utilize std async tasks to implement a complex algorithm like this. And that is the purpose of this implementation and that is the purpose of this video. Thank you very much.